In addition to pulleys, we also have to consider springs as special mechanical elements. Recall from Chapter 3 that we had these definitions for linear springs. A linear spring is characterized by a spring constant K, and it has units of force per unit length. In addition to linear springs, we now also have torsional springs. These are springs that exert restoring moments instead of restoring forces. These are also often helically wound elements, but the load transmitted is in the plane of the projected helix rather than normal to it. The result is a restoring moment instead of a restoring force. A clothespin is one example of an assembly whose two members are connected with a torsional spring. In these cases, the restoring moment can be represented as the product of a torsional spring constant and an angular displacement. This requires the torsional spring constant to have units of moments per degree or moments per radian. As a radian is a dimensionless measure of angular displacement, we might also say that the torsional spring constant just has units of moment. So whereas a linear spring has a spring constant with units of, for instance, pounds per inch, the torsional spring has a spring constant with units of inch-pounds. Some examples of linear and torsional springs are shown on this slide. We now take a look at a couple of examples involving the brake handle on a bicycle to contrast the free body diagrams of members supported with these different mechanical elements. Before we get to these problems, we'll just talk about the mechanism that's in place here. Our focus is going to be on the brake handle, which is shown in the pink or light red shading. We have a fastener at A, which is intended to permit rotation about A as a mechanism. When there's no force applied to the brake handle, the design of the mechanism is such that we want the brake handle to be pressed up against this stop at G. So one of the things we're going to find is that whether we're using a linear spring, as in this case, or a torsional spring, as in the next slide, the stationary unloaded configuration of the brake handle is going to be such that the system pulls the brake handle against the stop at G. So when we look at the problem statement, we're going to see statements like this. We want to determine the force P needed to begin motion of the brake lever. So you can probably see from this that P is going to tend to impart a moment, a clockwise moment about A, and the threshold required to begin motion of the brake lever is going to occur when contact breaks at G. So when we're looking at the free body diagram in both of these cases, we'll have some kind of a load from the spring element, either in this case the linear spring CD, or in the next example a torsional spring that's tending to impose a counterclockwise rotation, but we won't include any contact force at G because the nature of the problem is that we're trying to determine the threshold force to just begin motion of the brake lever, so we're just breaking contact at G. Okay, so our free body diagram for this is going to focus on this enveloping surface. And I'm going to begin just by trying to make a crude sketch of the brake handle below. So we're going to actually have 4 locations where forces appear on this brake handle. We've obviously got the force P that we're applying out here at E. We have this essentially pin support at A, even though it looks like a fastener. We want this to rotate about A as part of the mechanism, so I'm going to draw forces AX and AY at this location. We have the tension at B, and then we've got the force exerted at C by the spring. Now, let's note that the problem statement tells us the spring has a 5 Newton per millimeter stiffness and a 20 millimeter unstretched length. And if we just look at the dimensions that are shown in the figure, with a stretched length that has a component of 32 millimeters in Y and 16 millimeters in X, whatever that stretched length is, it's going to be the square root of 16 squared plus 32 squared. It's going to be greater than 20 millimeters. So this is in tension. It's pulling C in such a way that it's pulling it against the stop. That's what we want it to do. So we're going to show it in tension. Before we do that, the other thing we'll make a note of is that just looking at the geometry with a rise of 32 millimeters against a run of 16 millimeters, the slope of this line of action, we could say, is making a 1, 2, root 5 triangle. And that will allow us to break down the force components of the spring in the x and y directions relatively easily. So I'm going to put a spring force here at C. We'll just note here that the rise over run is 2 to 1, and that this forms a 1, 2, root 5 triangle here. Okay, so we might note that if we wanted to find the reactions AX and AY, we could certainly use our force equilibrium equations, but in this case we're asked for the threshold force P that causes the brake handle to move, and we can actually get that by just using one of our equilibrium equations, and that is taking moments about A. So that's what I'm going to do. The spring force, let's first find the spring force. We have the stretched length is the square root of 32 squared plus 16 squared millimeters, and that is equal to 35.78 millimeters. And then the spring force will be equal to the spring constant times the difference between the stretched and unstretched lengths. So we have 5 newtons per millimeter times 35.78 minus 20 millimeters, and that gives us a value of 78.89 newtons for the spring force. So now we'll take the sum of the moments about A and set that equal to 0. And we can see from the location of C relative to A that both the horizontal and vertical components of the spring force will exert positive or counterclockwise moments about A. T will also exert a counterclockwise moment about A, and then P will be the sole clockwise or negative moment about A. For the horizontal component of the spring force, we have 1 over root 5 times the spring force, and that has a moment arm of 32 millimeters. The vertical component is 2 over root 5 times the spring force, and that has a moment arm of 14 millimeters. The tension has a moment arm of 56 millimeters, and then we have minus P times its moment arm of 90 millimeters equals 0. So if we plug in numbers for the tension and the spring force and rearrange this, we can get the following expression for P. And if we calculate all that out, we get P is equal to 42.2 newtons. So in this third example, we have almost an identical problem involving a brake handle, but instead of having a linear spring that's tending to pull the brake handle against the stop at G, we have a torsional spring at acting essentially at A that's doing the same thing. So in terms of loads applied to this, we again have our force P that we're interested in. We have our tension T, again, that we know up here at B. We have our forces AX and AY. And then we have a torsional moment from the spring. And we'll use the information in the problem statement to figure out how large that is. So we're told that the torsional spring has a 15 Newton millimeter per degree stiffness, and that it's pre-wound by 90 degrees. Now what that means is that the restoring moment in the configuration that we're shown here is the pre-wound turn of 90 degrees times the spring constant of 15 Newton millimeters per degree. So in this case, the moment of the torsional spring is 15 Newton millimeters per degree times 90 degrees, and that's equal to 1350 Newton millimeters. So again, we can solve for P by taking the sum of the moments about A, setting that equal to 0. We have our torsional spring, we have our tension, which we know, again times the moment arm of 56 millimeters, and then we have our clockwise moment from the force applied to the brake handle, which is P times 90 millimeters. And there, again, P is going to be equal to the tension T times 56 over 90 plus this restoring moment from the torsional spring divided by 90 millimeters. And the result in this case is 33.7 newtons. Finally, another special mechanical element that will present itself on many occasions is the gear. There are a great variety of gears used in a wide range of applications, and those of you pursuing a mechanical engineering degree will eventually see many of these applications. For now, we'll restrict ourselves to gear sets that can be represented as planar elements. These are spur gears, and the meshing of gear teeth permits transmission of torque from one gear element to another. Generally, we'll talk about the forces between spur gears in terms of a coordinate system tangent and normal to the gear circle being this circumferential line that goes through the gear teeth. The tangent force is responsible for torque transmission through the gear radius. The magnitude of the normal force tells us something about how hard the gears are pressed into and pushing away from each other. Note that the normal forces have lines of action that go through the spur gear's centers, so no torque is associated with the normal forces. Although including the tangential force component is crucial in gear problems, including the normal force is optional. Whether we do so or not depends on how the gears are supported. Often, we'll find each gear is supported by its own bearing. In that case, we usually neglect the normal force between gears as small compared to the tangential force. In some cases, as in the arrangement shown here, neglecting the normal force component isn't possible. In this case, the small gear is not supported by anything, so its only means of support is through the interfacing gears on which it's sitting. The illustration shown on this slide refers to the track as analogous to a gear with an infinite radius. Although this seems like a contrived example, there is an important class of problems like this in the rack and pinion steering mechanisms in cars and trucks. We end this section with a final example where we are raising and lowering a flagpole based on a mechanism that rotates about the bearing at A. The fact that there is a bearing or pin at both A and B implies that each gear receives the bulk of its support at those locations, and therefore that the normal force between the two gears is negligible. When we draw a free body diagram for the sector gear, then, we will include just a tangential force component at C. Let's look at the solution for the rest of the problem. Our isolating surface for this rigid body will look like this. We'll be cutting through the interface between the sector gear and the smaller spur gear at C. We'll also be cutting through the bearing here at A, which is where this sector gear, where this rigid body is supported. So our free body diagram for this will look something like this. Here's A, and I'll draw an AX and AY component at this location. And then again, I'll draw just a tangential component at C because we're assuming the sector gear and the smaller spur gear are both supported at their bearing. So we're neglecting the normal force. And then we have the weight at the top here of 500 newtons. If we take the sum of the moments about A and set that equal to 0, we can get C directly. So we have a counterclockwise or positive contribution from C through a moment arm of 200 millimeters or 0.2 meters, and a similar counterclockwise or positive contribution from the 500 Newton force at the end times a moment arm of 3 meters. And that tells us that C is equal to minus 3 over 0.2 times 500 newtons, and that number turns out to be minus 7,500 newtons. So C actually goes in the other direction. It acts in the negative x direction. And then we can use force equilibrium to find the reactions at A. So we simply have AX plus C equals 0, and that tells us that AX is equal to minus C, or AX is equal to 7,500 newtons. And in the vertical direction, we have AY minus 500 newtons equals 0. So AY is just equal to 500 newtons.